All right, welcome all. So you have done well in the exercises, and there are some people who clearly gave up early on. There's 3 people who are just sub-threshold, so they should try hard for the last exercise, and we'll send them an email. And the others are fine and have earned the right to have an exam. All right. Now, today, so I promised I would tell you about the principles of modern architectures. And I am reneging on the promise for today and pushing this off for a little bit for the following reason. There is currently a line of work which I think is interesting and which brings us back to the first half of our lecture, which so far seems a little disconnected from what we're doing these days. And I want, instead of having regular exercises for the remainder of the semester, I want to give you the chance to have a go at something new, okay? So new in the sense of 1990s meet 2016. New in the spirit of California Gold Rush, you know. So right now we're still in this phase where, you know, whatever you do in neural networks, or almost whatever, it's a first, and people have these crazy publication cycles of, you know, 2 weeks old is old, and 4 weeks old is way old, so we see amongst these authors here. A few people, you know, they're even a bit older than I am, who remember, you know, things from an era before neural networks, and now they're trying to to bring that together with neural networks themselves. What I want to present to you today is something that, as far as I know, at least one of these groups is striving to do, but has not done yet, and the others haven't had the idea yet, or as far as I know, haven't started working in that direction yet. But to the best of my knowledge, this is not published yet, okay? And so what are all these 4 papers about? They talked about, they all think about rotational data augmentation. The last time we met, 2 weeks ago, I discussed the virtues of trying to generate more training data than you really have, and by sampling the manifold of images. And rotation in particular is useful for some types of images, but not for all. So if you think of street view scenes, rotational equivariance or invariance does not make sense, because we want to exploit the knowledge that the sky is on top and the road is on bottom, and you know, if something is gray and on the top, this means bad weather, and if something is gray and on the bottom, it means we can probably drive there. Okay, so in that kind of image, we don't want this rotational invariance. But if you remember my favorite images, you know, the one from connectomics, there is no up and no down. It makes sense to have a network with no preferred orientations. Now, the cheap way of achieving this is, the lazy way of achieving this is to rotate your input data along with the training labels that you have, and you know, train on this enlarged data set. The good thing is you can just use your standard architecture, and you don't need to know anything about steerable filters and whatnot. The bad thing about it is that the resulting filters are still not guaranteed to be rotationally invariant. So if you look at the learned filters, what you would expect is that you find a filter, let's say an edge detector, and that you then also find the rotated versions of that filter. But if you just present your network with many rotated images, there is no guarantee that these filters will exhibit this kind of symmetry that you would expect to find on first grounds. Yeah? Because the neural network will find into some local minimum and it will do something reasonable, hopefully, but it will not really have this perfect symmetry that we know about and that we want. And I find that disturbing for aesthetical reasons. Okay? The hope is that on small training data, you may even do a little bit better if you really enforce the symmetry. But to me, primarily, this is about doing things right. Okay? Now, these 4 papers here, they all talk about how to achieve this equivariance or invariance with regard to images that are rotated by 90 degrees. So if we look into some of these papers, they tell you explicitly, I don't remember in which one there was a nice figure, some of these papers will tell you explicitly that what we want is a weight sharing, namely the weights of one filter should be shared with the weights of the same filter rotated by 90 degrees. Yeah, this is a very, this is a good starting point, but it does not work well for arbitrary angles. Because if I talk about rotating around 90 degrees, this is easy. But if we talk about rotating by 21 degrees, you have this difficult interpolation problem, and things get a little bit trickier. And these papers, which came out, so one was published at ICML, which I attended last week. One came out on Archive in June of this year. One came out in April this year, and the date of the other I have forgotten. These papers stop short of doing what I would like you to try and do. Okay? So we want to enforce this symmetry from a start. And when we talked about steerable filters in the beginning of the lecture, we had a different viewpoint. I said at the time, take an arbitrary filter and then vectorize it. So my vectorized filter will be one column, and then rotate the filter by a little bit and vectorize it again. And in this way, we constructed a matrix. And then we did SVD, a singular value decomposition on this matrix. And we found a couple of basis filters. So for example, of rank 3. And then if you remember, I also argued that the coefficients on the right-hand side that tell me how I can synthesize a filter at an arbitrary rotation in terms of a linear combination of these basis filters, I argued that these are actually complex oscillations. And I said why that had to be the case. I also said at the time that these basis filters here, the basis filters themselves don't look steerable at all, because they are sorted by the size of the singular value, and they don't look nicely symmetric at all. I then also showed how nicely symmetric filters can be synthesized by taking the coefficients here at regular intervals and putting them into a rotation matrix and so on. But the starting point at the time was, give me any filter and I will make it steerable for you. Today I want to take a different route, namely I want to use a parametric representation for my steerable filters, so that in the backpropagation I only need to learn those parameters. Okay, and this is what the next longer bit will be about. So I am deciding arbitrarily to create my steerable filters as follows, by taking an angular part depending on some angle phi, and a radial part depending on some distance d from the origin of the filter. So I'm expressing my filter in terms of these polar coordinates, where phi is the how is this called, arctangent. Here I'm using the atan2 function, which converts two coordinates x1 and x2 into an angle. And d, I use that as, or parameterize it as a squared Euclidean distance. Okay, and this is now my basis filter B at coordinates x1 and x2, and I will add a couple of parameters in a moment. For the radial part, I will want something that lets me decide, how broad my filter is or how big my filter is. For the angular part, I want a behavior that, is periodic along this angular direction phi. Yeah? So I'm using here an index small k to count the number of oscillations that I want as I go around a circle. And let me put the zero angle at this position here. So this is where I start. And I'm now going to use a cosine and a sine. And I will have zero crossings here and there. So the cosine in this angular picture would look something like this. And the sine in this angular picture would look something like that. So what I'm drawing here is just, a fancy version of a cosine and a sine. For this to make more sense, maybe. So this is now my axis phi, and this was from 0 to 2 pi. Let me draw this in a way that's more usual. Okay, so the cosine. How many boxes do I have? So here's my zero crossing. I'm trying really hard here to make a nice cosine for you. All right. And this would be the corresponding sine. Okay, and this is just a different representation for what I've tried to draw above. Okay, so the zero angle was here, and this was 2 pi. Okay, so this was one rotation in this, or one oscillation in this polar dimension. And I'm now doing this, for the sake of example here, I'm doing this up to 3. And I think this will help our intuition. Oh no, now it's getting difficult. This is I hope this is right. I didn't want 4 lobes, I wanted 3. Sorry, this has been wrong. Try again. Okay. Okay, we can do this for higher orders, of course. And it will. So if I combine these linearly, I can, for example, produce something like this. So let's say one big lobe in this direction, the smaller one there, and an intermediate one here, something like that. Yeah, so this would be one possibility, and it's a bit hard for me to draw in the spatial domain what this filter would look like. So if I sum up these 3 in a weighted fashion, this is what I could get out. Okay, and it will be convenient for me if I am combining this by taking the first row as real part and the second row as imaginary part of my basis filters. And in that case, everything that I've written here is simply e to the I phi k, with k as written above. Okay, and then I can say that my basis filters I'm making them depend here on x1 tilde, x2 tilde, and a few more parameters. I'm defining this as the angular dependence. So this is what I previously called ang of phi. Now I'm multiplying this with some radial part times rate of d, and for the radial part, I can now make an arbitrary choice. So, for example, the Bessel functions or the would be something that makes sense. Something else from physics that you would prefer? I'm not going to write it down now, I'm just asking. What would you use for the angular dependence of your filters? How would you parameterize that? Yeah?
I think there's some kind of these polynomials times the Gaussian formula. I think it's called Laguerre polynomial.
Yeah, Hermite or Laguerre, one of the two. Yeah, so
I think it's a similar concept.
One of these, yeah. Okay. So I think what we want for sure is that for large d at some point this should taper off, and we also want to have the possibility. So we want it to be 0 at very large distances, we want to have the possibility for it to be 0 at small distances, so that we can query information at some point away. We also want it to be able to be non-zero at the origin. So what I thought I would use is just a difference of two Gaussians here. This is random, yeah, and there's no probabilistic interpretation associated with this. But if I take a broad Gaussian centered at 0, and if I take a narrow Gaussian centered at 0, they're unnormalized, so they both go to 1 at 0. And if I subtract one from the other, then I obtain something like this. Yeah? So I have two parameters, and by adjusting the two parameters, I can have something that's further out or closer in. Yeah? So I'm arbitrarily deciding that rad of d here should be e to the minus okay, what are all these numbers? So I have some additional arguments here. These are, so sigma 1 and sigma 2 are just the long and the short standard deviation, and I'm indexing them here with capital and small k because these are the indices that I also have up here. Yeah? And I'm sorry, I should have written sigma, excuse me, I should have written sigma kk, and I'm underlining this to stress that it's a vector, in this case a vector comprising two numbers. Okay, so I would say to write my steerable filter as a product of an angular part and a radial part is not so arbitrary, because, as I pointed out in the first half of the semester, these angular functions, they must always be complex oscillations. So I would say fundamentally this factorization makes sense, but the choice of the radial part here is completely arbitrary. And you can think of something better here. Now, so this number here is a complex number for each and every choice of the arguments of this function. Okay, and now what's this small and capital K about? The capital K here, you see on the right-hand side, the only dependence on capital K is in the choice of the sigmas, because I may want, so fundamentally, so small k here I'm using to indicate how many oscillations do we want as we go around the circle. And well, small k ranges from, we can decide if it should range from 0 or to 1, but it goes up to capital K. And I may wish to design several filters which have a different radial distance dependence for these different capital Ks. So, for example, filters that have a very high angular resolution that only makes sense in combination with a big field of view. Because on a tiny field of view, I cannot even, so in a very tiny field of view, I only have 9 pixels, and 9 pixels cannot give me an incredibly high polar resolution. So to get a high polar resolution, so to find very precisely the angle at which a line, for example, is oriented, I need many pixels, and that means I need big sigmas. But maybe I want to measure the low angular resolution content on a much smaller scale, and for that I may want to use a different sigma. So this is why I'm writing the capital K here. Okay, before I go on, maybe this was too trivial for you, these pictures, but just to build intuition, let's plot this basis function in a spatial domain. Yeah? Let us plot, let's say, B. Let's plot B of x1 tilde, x2 tilde for, I don't know what k, but let's say for small k equals 1. And here I'm using values, let's say, of 5 and 3. Can you describe to me what this filter will look like in the spatial domain? No? Yeah? Go ahead.
I think it would be just like a little bit like gradient filter, a derivative filter
Mhm.
in the x1 direction, and it's negative on the negative x1 side and positive on the positive x1 side.
Exactly. You're talking about the real part here, yeah? So let's say I'm plotting the real part of this filter, yeah? And it's just like you describe. I have a positive part, which is maybe, even a little bit, maybe it even looks a little bit curved. I'm using green here for positive, and I'm using red for negative. It would look something like this, huh? And we know that we have a zero crossing on the x tilde 2 axis, yeah? So there it must be strictly 0. It's large on the right and left side, and yeah. So this is now the product of what we saw up here. It's a product of this guy with this distance, or with this difference of 2 Gaussians.
I wanted to ask, why do we, with our choice of this difference of the Gaussians, we enforce that it's 0 at 0 distance, right? Why do we want this?
So I can, if I make sigma 1 so large that it is practically uniform across my mask, and if I give sigma 2, a normal value, then what I end up is still, it would still be 0 at the origin. Huh? But if I make it vice versa, if I make if I give sigma 1 a normal value, and if I make sigma 2 very, very large, then I would get out a negative Gaussian, right? No, it would still be 0 at the origin. So I think there is no good reason why we shouldn't have a filter that can be non-zero at the origin. One interesting case here is if we set k to 0, then I will have no polar dependence, so I would get out just an annulus, I would get out a circle, and by choosing appropriate values of sigma 1 and sigma 2, I could make it such that the circle is only missing its central pixel, but it would still be 0 at the origin. Yeah? So we cannot, with this parameterization, we cannot create a strict low-pass filter. And to do that, I would need an extra parameter, which I did not want to introduce here, but maybe one should. Huh? So one could have an extra parameter, for example, multiplying the second term here with, so there was a, by the way, there was a 2 missing, it's sigma kk2 squared, and I could multiply this with sigma kk3. And I've called this sigma now just for convenience, so I don't need to change the rest of my formula.
Maybe have an idea. Doesn't it have to be 0? Because if we just look at the angular part, we have for this central part, there are several possibilities. Every angle results in the same point in the origin, and therefore
you are right.
To choose 0 then.
But you're right, but I was thinking about the small k equals 0 part, you know? So where we really want low pass filters. Other than that, yes, you're right. To avoid ambiguity, we have to be 0 at the origin. Yeah? All right. Good. So this is what this filter would look like. Then the real part of it, and if we take, if I take a higher order, then I would have a negative here and negative there, and a positive here and positive here, and so on. And by taking linear combinations of these, we can create really strange filter shapes. This in itself does not talk about steerability yet. It just talks about what these filters look like in their standard orientation. Now, okay, so these are the basis filters, and I now want to take, I now need to actually convolve it with the image. Yeah, so I use B for basis filter, and I'm using C just because it's the next letter in the alphabet, but it also matches convolution. Yeah? So now convolve the basis filter B with the input image, which I'm calling G. And the result here is C at location x1 and x2. And I now have a new parameter here, capital M, namely how big do I make my filter mask? So far everything has been analytical, and now I enter the discrete world of digital images where pixels are indexed by integers. So I'm having here x1 minus x1 tilde, x2 minus x2 tilde, and a few more arguments multiplied with my image G. Sorry, I need to turn around the sign here. Because otherwise it would be correlation and not convolution. Sorry, let me do this differently. Yeah, because my filter, because my filter was only the way I defined my filter. I just want to have here x1 tilde and x2 tilde, and it is on this side that I'm writing x1 minus x1 tilde and x2 minus x2 tilde. Okay. Good. So this is now, these things C are now as big as my original input image, give or take a few pixels at the border, depending on what border treatment you use. And now I want to actually create my funny filters by combining the basis filters in a linear fashion. So I'm using d of x1, again d just because it's the next letter in the alphabet. And I'm now using some weight indexed by K and L, and I'm multiplying this with these images that we have just produced. And so what we have here is a linear combination of my basis filter bank outputs. And because convolution is a linear operation, this would be this. This is the same as the output of a filter, which is a linear combination of the basis filters with the same weights. And when I say output of a filter, I mean output, or if I convolve this filter with the input image. Okay, so if I choose appropriate values here for these W's, I could, for example, produce this funny filter that I created here just for illustration. So choosing appropriate W's would give me this filter, or if I use some other W's, I could produce a spaceship, Enterprise, whatever, any filter that you like, and I'm only plotting here the polar part, because if I factor the radial part in, it becomes even a bit more complicated. Okay, so far so good, except that this whole business is not yet steerable. So we have created some basis filters. We have convolved them with the input image that gave me C, and I have now linearly combined those filter bank outputs with these W's, but so far no steerability is guaranteed. And during the break you can think about how we now make this whole thing steerable. Okay, so far there was no steerability. Yeah? So now comes the crucial point, and I've tried hard to draw you more nice sinuses and sines and cosines here, because I wanted to emphasize that these coefficients W that I've been writing further down, they really are the coefficients in a polar Fourier transform. So the W from below, I called them, what was it? W K KL. Those are the coefficients of a polar or an angular Fourier transform. And for the sake of completeness here, I should probably still draw the zero frequency after all. So 0 would be here. See if I can copy some of these nice circles. So for the zero frequency, we have a purely real part. And zero imaginary part. Okay, the number of, here I drew 4 supporting points, but that number was arbitrary. Okay, so I've painted all these sines and cosines because we now come to the question, let's say here for our starship filter, this one, how many directions do we need in order to have no loss of information when we're using this Steerable filter? So let's say that I know that this is a great filter. Now, how many rotated replicates of this filter do I need? When we used the SVD at the time, we simply used 360 rotations. That was an arbitrary number. 360 was as good as infinity, as far as we were concerned. But in this concrete example here,
I mean, with the SVD, we could also check how many we need to perfectly reproduce it. So here we could just do a SVD again and then see how many non-zero convolutions we get.
Yeah, we could do that. And what would you expect to see?
I mean, for this filter, maybe, if the back of the starship is symmetrical, 3 or something, 4, I don't know.
So I said that both these starship filters that I've shown here were synthesized only from the basis functions that we saw here, by just taking different weights in the linear combination.
What was your question again, precisely?
My precise question is, let's say I'm choosing some weights to linearly combine these basis functions into that starship filter. How many rotated versions of this filter do we now need to make it steerable? Now remember, definition of steerable means that we need a couple of basis filters such that we can synthesize the output of an arbitrarily rotated filter from those basis filters. And now I've used the word basis filter twice. Yeah, so in the last 45 minutes it was basis filter were those. Yeah, go ahead.
Yeah, we repeat K compared to one.
Not quite. Yeah, but getting there.
I think it depends on K.
Yeah, on capital K. Yes. So here I used capital K equals 3.
No, I mean on small K. because the small k equals 3
No,
filter,
K-
you can rotate.
Small k always goes from 0 up to capital K. Yeah, sorry.
But you don't want to rotate these single filters or?
No, these basis filters I don't want to rotate.
Okay.
Because we can think of each of these basis filters. If I'm just using, let's say, this filter and nothing else, then in polar space, this is an extremely band-limited signal, namely a band-limited signal which used only a single frequency, 2 polar, periods per rotation. And for such an extremely band-limited signal, I only need 2 samples, namely, this one and that one. But now I'm using I'm always saying that small k always goes from 0, 1, 2 up to capital K. And in this case, I've used capital K equals 3 to generate these 2 fancy filters. So how many rotated versions do we need? Capital K was close, yeah.
2K. Okay. Because we also need to assign the phase shifted parts.
Yeah, not quite, but this is closer still. This is the guessing now. Okay, everybody's oscillating between this is too easy and this is too hard. So, just count the circles, okay? Sorry. It's 2, 4, 6, 8. Yeah? For capital K equals 3. Yeah? And the argument is the same as, this is why I painted this picture here. The argument is the same as with standard Fourier space. Yeah? So if I have up to 3 periods, I need to consider the frequencies 0, 1, 2, and 3. And I have a real and an imaginary component for each, so it would be 8 samples. If I know that my signal is real, then I know that one of the coefficients is going to be 0, namely that one. Yeah? The imaginary part of the 0 frequency is 0 if the signal is real, because of these. You can think of it by just looking at the basis function, or you can think of it in terms of the symmetries of the Fourier transform that we discussed. Yeah? So we need, if I synthesize a filter from up to capital K basis functions, I need 2 parentheses capital K plus 1 filters. Yeah, so we know now that L goes from 0, 1, 2 up to 2K plus 1. Okay. And now about the steerability. Where does the steerability come in? So capital K here was the max polar frequency. Small l was by how far do we want to rotate our filter. Sorry, if I start at 0, this formula is wrong. The formula is correct only if I start at 1. So I should have 2k plus 1 without the parentheses. But the question is now, how about the steerability? Where in this equation does it come in? Yeah?
So omega is responsible for it, right?
Mm-hmm. Yes, and how?
Yeah, it should be, I'm not sure, but it's a complex number, and phase shifts our basis filters by a certain amount,
Mm-hmm.
depending on the stereo degree we want.
Exactly. So I want coefficients that create me my basis filters. W capital K small k 0. This is my, starship, for example. It was, some pretty asymmetric starship. You know what I mean? Sorry, I'm not very good at drawing. And now we want to put this into relation with, you say omega, I say W capital K small k L. And like you say, these are now the rotated versions. And because I'm working in this complex space, rotation means I'm multiplying with some complex number. And the complex number is L divided by 2k plus 1. Okay, so this is the steerability condition, namely sorry, this was a terrible starship. I'm having, some filter with a rotational character that I liked. Let's say this was the rotational character, and I now want to synthesize some rotated version of this. Somewhere I can rotate. Okay, and this rotated version will now be synthesized from the same basis filter bank. Yeah? If you go back through the equations, I only compute the convolution of my input image G with my single set of basis filters, at least for a given radial dependence, single set of basis filters once, and now I only tweak these coefficients with which I linearly combine them. And this tweaking is in a very simple fashion, namely by multiplying with these complex numbers. So what this means is that in this whole equation, let's say we have trained a filter bank that with a very high angular resolution. Let's say capital A is 8 or something. Then if I did this naively, I would have to compute, let's say of the order of 64 different coefficients. But here, on the right-hand side, there are no parameters other than, which rotation L am I interested in. So now I need to learn these coefficients only once. I need to learn only my 8 or my 16 coefficients. 16 coefficients if capital K was 8. I need to learn these only once, and other than that, they're just related by this shift. And now, by the way, if you now put, if you put K equals 1, then you recover, then I only get 4 distinct orientations, and in this case, the whole in this case, I get this matrix here, and what I see, this is my matrix W, and then what I see is that if I have A, B, C, D here, I will get A, B, C, D, A, B, C, D, and so on. So what these papers that I cited initially, they have solved the capital K equals 1 case. And now you have the chance to solve it for arbitrary K. Okay? And this would allow you to go from 4 filters or from 4 principal directions, or from 4 directions to arbitrarily many directions. So, in terms of the neural network, this equation that we have here, I can just directly insert this up here. And that means that the only filters or the only parameters that I need to learn are those. I only need to learn, or however rotated my input image is, it will always contribute to the refinement of my 0 rotation starship filter. Okay, and that happens through weight sharing. All these rotated filters use the same basic weights, WKK0. Yeah.
I'm a bit confused about this rotation factor. So should it be 2 pi times L over 2k plus 1? Or if not, I don't understand why. Because I would expect that if I go through all the L's, I complete 2 pi rotation.
It should be, I think this is with the parentheses, yeah, so this should be 2. Would you be happy with that? Mm-hmm. Okay. And then we can cancel the 2. Thank you. Yeah.
So the L is our, the different L's are different steering angles we then get for.
Yeah.
Well,
Mm-hmm.
why do we only have 2k plus 1? I mean, we could get arbitrarily many steering versions of our filter, right?
Yes, but this is like oversampling a signal. Yeah? So if you think of Nyquist's theorem, if you have a band-limited signal, it's enough to sample it twice per period. And by definition, so by the way that we construct our filters, this signal C will be band-limited in polar direction. All right. Good. So, and then, by the way, so far this is not useful for neural networks because all of this is completely linear so far. Yeah? So we need the nonlinearity. And now we can, we need a nonlinearity. We can invent on any nonlinearity we like, but there are some that make a lot of sense here. Huh? So now add the nonlinearity, and for example, one that I think makes sense is to say, what was the filter response at that location in the image regardless of orientation. So that would mean we take the max over, by the way, I used small d once, which is a little bit bad. Way up I used small d to indicate squared Euclidean distance from the center of my mask, and now I use small d as just the letter after C in the alphabet. I'm now using the second d. Yeah, sorry about this. So this last d was a function of x1, x2, capital K and L, and I could now take the maximum over L. So this would say how strongly does my steerable filter bank or steerable filter respond to that location of the image, regardless of the angle that came out. Or if vice versa, if we were interested in the location, then we wouldn't use max, but we would use the arc max with respect to L. Then we would get out the orientation itself. Or we could say, for example, we want to combine this with a max pooling. So this filter here, let me first write this down. Get it's equivalent to getting a filter response maximized over all input image rotations. But in this case, the input image would not be rotated around its center. No, the input image would be rotated around the pixel where we're currently computing the response. Yes?
So if I take, for example, just the derivative delta, we know that it's steerable from just having the x and the y derivative. So here if I take, for example, if I have a derivative in so x equals 1, y equals 1 direction, if I just take the maximum, I won't really get the information that the derivative is actually larger in this diagonal direction. So shouldn't I take sort of a, I don't know, weighted sum or?
You are right. So the phenomenon is the following. So this is where we sample our signal. We sample our oscillation at 4 points, and if we happen to have our oscillation with which we assume has a maximum frequency of 1, if it happens to be perfectly aligned with my sampling pattern, then the biggest sampling response that I get is also the maximum of my signal. Yeah? If on the other hand I have a phase shift, then the maximum is here, but the strongest responses that I get are only there and there, or the strongest response would be this one, but the maximum is that one. Yeah? So I could use a more refined maximum operator, which in this band limited signal finds the actual maximum and outputs that. And that would be possible. I just didn't want this added complication here. Yeah? So I'm approximating the absolute maximum with the strongest coefficient or response that I find. Is this picture clear, by the way? So this is this would be from my 4 steerable filters, the outputs of those 4 steerable filters measured at the 4 bars, and the continuous signal shows me the real behavior of in this case a signal with maximum k equals 1. Okay, so if we want to combine this with max pooling, we could do something like this. We could say we want to find the maximum over both L and small shifts in both directions, and we could say this is the x1 plus S1, x2 plus S2, and L. And then S1 and S2 would be, let's say, from minus some number to plus some number. So this would be a simultaneous max pooling over space and rotation. And we can think of many other nonlinearities that could make sense to use. Okay, and now at this point, like 90 minutes later and a few equations later, we have only arrived at a single layer of our neural network. Okay, So we now have a deluxe convolutional, rotationally equivariant layer of a neural network. So this combination of the steps, input image G and convolve it with B to get C, and weight it to get a D, and then push it through nonlinearity to get an E. That is now the output of my first layer in the neural network. And now I could use many of such layers to get a deep neural network if I like. Okay, so at this point here, we now have a single, let me call this steerable CNN layer. Okay, now I have a few more comments on what does this computation graph look like that we use in neural networks. Last time when I started discussing neural network architectures, I drew pictures like this. I said we take the input image G and then we convolve it with various filters to obtain multiple feature maps. So here I used a one-dimensional input image G. This box here was meant to represent many feature maps. And then I said, and then we can squeeze them through nonlinearity and get even more feature maps, maybe at the same spatial resolution, and whatever else happens afterwards. Now, here, these graphs are a little bit sparse, so I want to draw a different picture here. So I'm using G as an input, and now I'm showing explicitly for the case of k equals 3, the different basis images. So let's say this is my basis image for small k equals 0, small k equals 1, small k equals 2, and small k equals 3. And this entire thing, these are my maps C that result when I convolve my basis filters B with the input image G. Okay, so at this stage I have C, and I can now obtain various Ds. To not clutter the whole thing with indices so much, I pretended that for capital K equals 3, we take a single I just used a single set of weights. Yeah, so what I used so far was to say, okay, we now combine these linearly to obtain a D, and now not just one D, but in fact, what was it? 2k plus 1 or something of them. I think without the parentheses. So this was 2k plus 1 if I start counting at 0. These are now the different, so these are all filter bank outputs from the same filter that has been rotated. And then I squeeze it through this nonlinearity. For example, if I use the first nonlinearity that I described, then I simply obtain, I max over these over this dimension of small l's. So I had used small l to index this from left to right, and then I get out a single response image. But now in reality, as you've seen here, typically we want to get many features. So other than just using this starship filter, I can synthesize other filters that I like. And importantly, even though I synthesize them from the same basis filters, their response will be fundamentally different. So these are synthesized from the same basis filters, but I can synthesize different filters. I could try and synthesize a filter that has, just one lobe or two lobes or something, and I can then put it through its nonlinearity also. And for that, I need an extra index that I wanted to spare you before. So, I could use an extra index, let's say an index I here, for the ith of these filters. Who's laughing? Okay. Okay. So this index I would now run across these different filters that I'm learning here. And these could be more or less than the number of basis filters. So here I've shown 2, but I could also, have 5 or something of them. And now, this is not the end of the story, because so far I only showed k equals 3, but I also have k equals 2. I have k equals 2, and for k equals 2 I would have small k equals 0, small k equals 1, and small k equals 2. And these filters here can also feed into those and in the other one further above. Okay, now it gets completely cluttered. This was for k equals 2, and then in addition I have k equals 1 and k equals 0. Yeah? So each filter can be composed out of filters, out of various filters capital K. And from the same set of basis filters, I can synthesize different filters with different responses. Okay, and all of these things that I've drawn here, taken together, they just correspond to a single set of feature maps in my CNN. And by this more explicit representation here, I wanted to show a little bit, how this computational graph is connected. So, if I draw a somewhat more abstract picture, we are back to the one on top here. Yeah? So here I used certain rotational filters, and I got out this. Now I could use many of these rotational filter backs one after the other. However, if I initially use filters that have a low rotational resolution, then probably it doesn't make sense to use very high rotational resolution layers later on in the network, because I expect the output to be already somewhat smooth. So that's a thing to keep in mind in the architecture. And coming back to these sigmas, we can now use different sigmas, so different radial dependence for these filters with their different capital K, if we like. And we can let the network learn these, of course. Yeah, so what we would do, we would initialize these sigmas with some reasonable value, and then using backpropagation, let the network fine-tune all of these parameters. So what are the human choices? The human choices are up to what capital K do I want to go? The human choices are how many of these kinds of filters do I want to learn in parallel. The human choice is what is the size of the filter mask, capital M, that I'm using. Actually, that is a choice that really follows from the choice of sigma. So I could say capital M is, for example, 3 times the maximum of the absolute values of sigma k, k1 and sigma k, k2. I don't need absolute because these are positive numbers anyway. Yeah, so then the filter mask would be 3 times the standard deviation of the bigger of the 2 filters that I'm using. Okay, and then we can do backpropagation. So there is a homework part and there is a project part. The homework part is derive the backpropagation equations from the rules that we've seen 2 weeks ago and from the equations that we've seen today. And there is nothing particular happening here. If rather than working with complex numbers, it may be a bit simpler, and anyway that's how it would be implemented on GPUs and such, to have the real and the imaginary part as distinct entities. Then this complex exponential with which we multiply isn't a complex number, but it then becomes a matrix. Yeah? So we would have each complex number becomes a vector, and this thing would be a matrix, just a rotation matrix in 2 dimensions. And I think everybody, I hope, can do that. I hope, because I haven't done it myself yet. But I don't see any so far I don't see any special difficulty in these things. And the project part is, if you like, then try and get this going. You are free in your choice of what family of steerable filters you want to use. So if you want to use a different radial behavior, this is fine. And if you succeed, then write it up in ICML format, and then if you're lucky, you have your first paper. Well, the ICML submission deadline is only a few months from now. Yeah? So because ICML was just last week. But because that is so far away and because this is a new network world, you should then put it on archive first. Okay. So I'm half serious with this. It's because I know that you also have other courses and other exams to attend to and so on. But to the best of my knowledge, what you've seen today goes beyond, what the published state of the art does. And here's your chance to go beyond that if you like. So if you do like, so everybody should try and derive the backprop equations. But beyond that, if you like to do this in the next, semester holidays, if weather is like this, then we would enjoy doing that with you. So then, rather than you burrowing in a hole and then reappearing 12 weeks later, it would be better if you talk to us, to see where you get stuck and if we have any hints for you. But you could actually make a contribution to the state of the art if you did manage, which would be very nice, of course. So before I close, any more questions from today?
I'm not sure that I understood correctly because the L, is it a parameter or is it when you do the maths?
Small l is not a parameter. So small l goes from 0 up to 2k plus 1.
So K is actually...
Capital K is the important parameter. Capital K determines what is the angular resolution that you want to use.
So by fixing your frequency, or your maximum frequency, you're also fixing the number of rotations you actually...
Exactly. Okay. Then thank you very much, and then we'll have a more conventional lecture next time with no dangers of projects looming and such. Okay.